However, I was realizing that the dimensional analysis and metric conversions went up to page 26. Oopsies. Y'all got a little shorter readings. So just kind of doing a quick overview. When you start looking at the chemistry, you're going to notice that there's this huge, when we were in physics, we saw the world from this macroscopic view, which made life so much easier because we could see things fly in the air, coming down, and all that good stuff. But when you start thinking about chemistry, it's actually a microscopic world. And so we got to really think about viewing chemistry in this atomic level. When we start thinking, what are the electrons doing? How are they moving? How are they reacting? How are they coming together? And so it's definitely a different mindset when you start thinking about chemistry in the atomic level. When we look at this, we've got an atom versus a molecule. I can look at an oxygen atom, a hydrogen atom. Anybody on the periodic table is an atom. Neon, copper, chlorine, all those. But now these guys don't naturally like to hang out by themselves. And so when you go and you mix oxygen and hydrogen, they form this nice little water molecule, which you have one oxygen atom and two hydrogen atoms. They come together, form a molecule. So an atom is just one part of an element that's going to stay true to its property based on the periodic table. And when you have two or more joined together, acting as a unit, you have a molecule. Now we can kind of take this and look at it in a more of a real world scenario, because oxygen doesn't like to hang out by itself. And for the most part, I always look at oxygen as like my girls. They always like to go to the bathroom together. And so oxygen is the same way. He doesn't like to hang out by himself. So he'll go and find another oxygen molecule and he'll mush himself together, and they always move around as a team, which is an oxygen molecule. It's also written as O2. This number right here is a subscript, and it tells you how many atoms you have. So this tells me I have two oxygen atoms. Perfect. I've got two little red spheres representing oxygen. I have two oxygens right there. And same thing with hydrogen. You have H2, tells you have two atoms of hydrogen. I can see my two bubbles right there. Perfect. No big deal. All right, now when I look at this, water, if you go and put some electrical currents to it, is actually going to have enough energy to break the bonds to separate the oxygen and the hydrogen atoms. Okay, and like I just said previously, oxygen does not like to hang out by itself. So when I break the bonds, oxygen's like looking like, where's my buddy? Where are you? Hello, I'm supposed to be a partner. And so that's why when you do have the splitting of water, you technically have two atoms of water that are going to split up. Okay, and so when these two atoms are going to split, you're going to have these two atoms of oxygen come together, and they're going to make a diatomic molecule. And now you have these hydrogens floating around. And so it might be these two that match up, these two that match up, those two. It can be all sorts of different combinations, because now they're floating around in space and they just randomly come together. Because just the same way as oxygen's looking for its partner, hydrogen's looking for its partner. And so as we needed two atoms of oxygen in order to form my diatomic molecule, and by default we have two hydrogens that attach to one oxygen atom, so now we're looking at four. So when they come together, we form these two hydrogen atoms. Now, let me see if I can get to my pen. Let's see, pen color. Let's see if I can write here. It's not letting me write. All right, and so really when I'm looking at this is kind of that balanced equation, because you're seeing two molecules of water will break down to form one molecule of oxygen gas plus two molecules of hydrogen gas. Scientific method, very important, and I know you guys have been seeing this since probably kindergarten. Really what it is, you've got scientists that are out there looking at the world and trying to figure out why things work. And so it's been happening forever. Now, the sad thing about it, and even since the beginning of time, if you read through your chapter, you saw that Lavoisier had done great things for chemistry. His dad wanted him to be more of a legal scholar, but he had such a passion for science and chemistry and made really good, accurate measurements that he started leading the way and actually even wrote the first chemistry textbook. But it's crazy to think that even back then, in the 1700s, early 1800s, things were still very politicized, and our scientists kind of had to be mindful of what they were saying, what they were doing. At the end, poor Lavoisier was still beheaded for his political beliefs. And so when you start thinking about science, we naturally look at our environment and we start seeing things and we start questioning and we want to know why. But for those of you guys who kind of keep up with the news, you're going to see there's always conflicting scientists saying about the environment, what's hurting it, what's damaging it. Should we be concerned? Should we not? And so you as a scientist, what you need to do is kind of do your own research. Look at the world, make some observations, and then once you're ready to start wondering, that's when you frame your question. And that's what kind of leads over to your hypothesis. And so we're scientists every single day, all the time. And, it's all about asking a question, experimenting, gaining new knowledge. And then once you have that experimentation, from there, now you need to go and kind of form a conclusion. And that's just the basis of science. And you'll see it everywhere. And this is kind of a nice little flow chart here. You observe, you form your hypothesis, you do experiments. Once you've done that, you start collecting data. And that data is going to go and refine your hypothesis and then you're going to kind of start forming your own theory on things. And then once you have your theories, you can start making some predictions. You can alter your experiments. You can modify your procedures if need be, and keep going. Now, there's going to be certain things that are going to be law. Like if I go and grab these keys and let go, every single time I get the keys and let them go, they're going to fall down to the ground. Okay, and that's going to be because of the law of gravity. It doesn't matter how many times I do it, it's going to be a repeatable observed behavior that will happen every single time. A theory on the opposite end, it's a tested hypothesis. It gives a really good explanation of some natural phenomenon. However, theories can change over time. Okay, this is going to be your prefixes for your base units. This one goes a lot higher than what we've done, but what I do want to point out to you is it follows that rule of 3. Okay, 18, 15, 12, 9, 6, 3. And then at that smaller ones, you go down by ones, 2, 1, 0. And you'll notice the same is true on the lower end of your metric stairwell. So you go -1, -2, -3, -6, -9, 12, 15, 18. You start doing those jumps by threes again. And so you just see them really, really small or really, really big. And so scientists are going to be using these prefixes here. So instead of saying 1 million meters, we can say 1 megameter. Okay, and so that's kind of how we use our metric system. And for the most part, most countries use the metric system with the exception of the United States. We're still kind of, with our English system and going. And it's sad because there has been some issues that we've run into. So kind of a little chemical connection. So we had Lockheed Martin go and build this spaceship that was going to go up to Mars to collect some data. Well, Lockheed Martin went and sent all their data using the English units, and it went over to the Jet Propulsion Laboratory in Pasadena, California. And those guys thought that all their measurements were in meters. And so when they launched it, they were expecting, to have a little bit of leeway because they had, room for the spacecraft to land safely. But because they were off on their units, they didn't make the correct conversions, and that spacecraft ended up crashing. It dipped 100 kilometers lower into the Mars atmosphere than planned. The friction of the atmosphere caused the craft to burn up. So that was just a very, 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 very expensive mistake to be like, oopsies, did I forget to tell you that? So be careful when it comes to units. It's an important thing to kind of be mindful of them. It's always important to put your number and your unit so we know what you're talking about. All right, difference between mass and weight. Mass is going to be the amount of matter in an object, and it doesn't matter where you're at. The mass will always be the same. So the mass will be the same on Earth, on the moon, Jupiter, Saturn, insert planet, whatever. Gravity, on the other hand, is going to be the strength of the gravitational field. And on Earth, our gravitational field is going to be larger than the moon, so you would weigh more here on Earth than on the moon. But if you compare the Earth to Jupiter, Jupiter is a lot more massive than the Earth, so the gravitational field in Jupiter is going to be a lot larger. So the weight does vary between planets, but the mass is going to be constant across the entire universe. All right, uncertainty. This is where we start doing a little bit of math. All right, a digit that must be estimated in a measurement is called uncertain. A measurement always has some degree of uncertainty, and that's because when we make our measurements, we can go to the certain number, but then unless it's like right on there, if it's floating between two numbers, we've got to kind of figure out, just kind of make a good estimated guess on what that number is, and that's known as the uncertain digit. And so when you look here, I know this picture doesn't completely match with this picture here. We're going to go ahead and use this picture to come up with the answer here. And so we want to look at the meniscus. All right, the meniscus is going to be that liquid curve, which is right down here, and that curved part is where we're going to make the measurements. And so this burette here, when you start pouring liquid down, we start measuring how much we've excreted into our beaker. We'll just say beaker for now. So we know that we've had 20 and then some. So when I look at this, we've got 10 little lines in between the 22 and the 21. So that means I know these lines are going to be 0.10. So I've got 20.1, and here's 0.2, and it's somewhere in between 20.1 and 20.2. And so this is where we kind of start going to that uncertain digit. And so we can assume that it's at 20.15. I could have said 20.16. You might be looking and say, oh, more like 20.14. If that's that uncertain digit, that depending on who's looking at it, we'll look at it slightly different. And so the certain digits goes all the way to the 20.1. The uncertain digit is at 5. Accuracy and precision. I'm going to go to the next little slide because it has this great bullet kind of demonstration of precision and accuracy. If you keep throwing your darts and every single time you're right here on this corner end, well, you've got pretty good precision because every single time you keep hitting the same exact spot, but you're not very accurate because you're trying to hit the bullseye. This guy right here is just all over the place. He's neither precise nor accurate. But this guy has good precision, but it's not accurate. But this guy that keeps hitting right around that bullseye is both accurate and precision. Now, to kind of take it back to something that we would do, let's say we're going to start making measurements and you get the mass of a copper 2 chloride solution. And let's say every time you keep getting 23.5, 23.6, 23.55, you're pretty precise. But let's say the actual measurement should have been 30 grams. Well, that tells me you are precise, but not very accurate. Okay, it could be a reading error, it could be an equipment error, it could be something. There's several different factors which could affect your accuracy. You're making very precise measurements because they're always the same, they're just not very accurate. And so that's kind of that connection there. All right, counting significant figures. Let me see if I can pause this. Okay. Alrighty, so now when I start looking at significant figures, I always look at it as Pac-Man. And so if I look at this number right here, and I draw my Pac-Man here, and I draw my Pac-Man here, any non-zero number is going to be like a ghost. And so if I change my pen color, let's make him blue. So this would be like a ghost right here. And a ghost right here. And another ghost. And another ghost. Does Pac-Man like to eat ghosts? He dies. For those guys who've never played Pac-Man, yeah. Pac-Man likes to eat the little pellets. And so right here, I've got 4 little ghosts representing 4 significant figures. If I go and look at this one right here and I do the same thing with my Pac-Man, well, here's my little pellets. He's like, jump, 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 jump. And then here's my numbers. And what did I say my numbers were representing? Yep, my ghosts. And so I come and I see, I'll make them pink now. I come see my ghost right here. And so Pac-Man doesn't like to eat ghosts. And so I drew two little ghosts. I've got two significant figures. Simple as that. If I look here, here's my little pellet. Same thing. Come to Pac-Man. All right. Any non-zero, I want to look at them as a ghost. And so if I, okay, here's a ghost. Here's a ghost. Here's my ghost. And so by default, that zero has, as it's one of those captive zeros, he's going to count as a significant figure. So I've got 1, 2, 3, 4. Okay, so I've got 4 significant figures. I like to play Pac-Man with them. Now, like here, Pac-Man is going to be slightly different because if you see that there's a decimal point right there, he's there for a reason, making these zeros significant. Okay, so this one, Pac-Man rule doesn't apply. But so the trailing zeros at the end of a number are significant only if it has a decimal point. You notice this one, 150 doesn't have a decimal point, so it only has 2 significant figures. Now, if I would have put like 150 and put a decimal at the end, then that means it's significant and it counts, so I would have 3 sixes. As you can tell, I can't write very well on this mouse pad. All right. Now, other rules for significant figures, if I have an exact number, then it's I don't have to worry about significant figures because they're infinite number. So like one inch is exactly 2.54 centimeters. If I obtain something by counting, then it's 9 pencils. If I'm using pi, it's infinite as well. If I would convert 1 mile into kilometers, well, when you go and you look at your formula chart, you're going to see that it says that 1 mile into a kilometer is 1.60934. Okay, but we usually see 1.609, and that's an estimate here. And so when we look at this, we would only have 4 significant figures here, right? And because we're getting rid of these numbers there. So just kind of be cognizant when you start looking at significant figures and calculations. If you round it to be a little bit, so you're not as, if you don't have that many numbers, you got to keep that in mind. Then you got to use that for counting for significant figures. All right, so other things, exponential notation. I know in physics, we were using the E. So we would say 3.000 E2. We were using that for shorthand so we can get out of the times 10 carried 2. Well, I can tell you when it comes to chemistry, it doesn't work. You got to use 3.00 times 10 to the second. Okay, we have a decimal point right here, which means all these numbers are significant. When we put into exponential notation, we got to have those 3 significant figures, 3.00 times 10 to the second. All right, 2 advantages on it. It's easy. When I start looking at my significant figures, it's really easy to say, oh, 3 significant figures. Cool. Secondly, especially when I have those really crazy numbers like 0.000000052. If I would have something like this. See, 1, 2, 3, 4, 5, 6, 7. Okay, it's 7 zeros. 1, 2, 3, 4, 5, 6, 7, 5, 2. Well, Pac-Man tells me that all these zeros are insignificant. So I really only have 2 significant figures here. If I would switch over into a different color, let's go red. Well, the rule is that the number in front of the decimal has to be between 1 and 9. And I look at here, yep, 3 is between 1 and 9, and that follows the rule. Right now, this 0 is not between 1 and 9, so I have to move my decimal until I reach that 1 through 9. So 1, 2, 3, 4, 5, 6, 7, 8. So my answer would be 5, 0.2, there's my two significant figure numbers, times 10. Now I made 8 jumps. Because this number is smaller than 1, it's going to be a negative number. Negative 8. Like it or and there's my answer. 5.2 times 10 to the negative 8. All right. If I look at significant figures in math operations, both of these rules are going to be the same for multiplication and division. So I'm going to look for the one with the least precise measurement, which I look at this one. This one has 4 significant figures. This one has 2. As this one has 2, it's the one that has the least number, so my answer should also have 2 significant figures. Now, here's the catch when doing all math operations. You want to solve your process going through the entire multiplication division set, and then your final answer is when you go and you apply the significant figure rules and also your rounding rules. So I look at here and I know I need to have 2 significant figures. So I'm going to stop there. I'm going to look at this 8 right here, and it's going to tell me what to do to my 3. Because this number here is larger than 5, that tells me to round up. And so that's how I get to my 7.4. All right, so if I look for addition and subtraction, okay, so this one's slightly different. So I'm going to look for the number of decimal places for the least precise. So I see this one has 3, this one has 2, this one has 3. Well, here's my winner. I'm going to go to the nearest hundreds. So once again, you're going to add all of them together, and then once you have your final answer, you'll go ahead and do your rounding. And so that's why I go to the nearest hundreds. My answer here is the nearest hundreds as well. All right, so just kind of a little concept check. When I look at this, I want to figure out how much. Let's see. You have water in each graduated cylinder. You add them both to the sample beaker. Assume all the liquid is transferred. How would you write the total number being reported? All right, so you look at this one, and this one's going to be as accurate as 2.2, 2.4, 2.6, 2.8, somewhere in there, about 2.9-ish. Okay, looking at the meniscus down here, and then you come and you look at this one here, and this one's going to be more accurate and precise. So this one is going to be not even a whole milliliter. So this is 0.5, 0.4, 0.3. It's a little bit shy of 0.3. When I go and I put these together, you're going to see this rise up a little. So I said this was about 2.9. My 9 would like to write. All right, I said this was somewhere about 2.8. Oh, sorry. 2.8. And keep in mind, I'm just estimating. When I do add this up together, I'm going to be coming up with somewhere around 3.18. Now, obviously, my uncertain digit, I was a bit higher than what these guys were coming up with. So if I would round, I would end up with 3.2. Okay. So, and that's kind of limited precision when you start talking about volume, because once you start having that uncertain digit and you start assuming what it is, it may not be completely accurate. So dimensional analysis, I'm going to go ahead and stop here. I know we said we're going to get to slide 40, but I know we didn't hit this on Friday with 1A, so we're going to push this over into Monday and Thursday for next week. Hopefully you guys got a good little piece. I'm going to go over to the Nearpod and go over some more sample problems. Hopefully that will also help you out. Alrighty guys, so now I'm on the Nearpod. I am on the student pace, so it's QCEZD. So I'll just kind of go through some sample problems here through the Nearpod. So chlorine gas, would that be an atom or would that be a molecule? If I'm saying gas, he's coming with his partner in crime. So if you are guessing molecule, good job, it is a molecule. Neon gas. Now he's a tricky one because if you think about it, he's a noble gas and he's got a stable octet. So he always travels by himself. So tricky, tricky. I know. He's an atom. Copper, you said atom. Good job. Atom. And then sodium chloride, that's the wonderful stuff we put on our salt. Yep, molecule. All right, so now rounding. Now, when I start looking at rounding, it says go to the nearest hundreds. So that means I'm going to look at these digits right here. And to round them, I'm going to use the number right after the number I want to round to. So I'm going to look at here. I'm just going to ignore everybody else because it doesn't matter. So now I just come up with my answer. So now this 2, what do I do? Well, if you said it's less than 5, you leave it alone. Perfect. 1.59. Perfect. Well, this next one, I've got a 6. Well, it's greater than 5, so that tells you round up. 2.99. All right, this one, some of you guys may go and look at that 9 and say, ooh, that 9 tells you to round up that 4, which means don't go all these extras. All right, so you want to ignore everything after that number that's going to make the deciding factor if you round up or you leave alone. And so when I look at it here, that 4, because it's less than 5, that tells me to leave alone. And so my answer is 5.74. Sorry, guys, I don't know how to write on this thing. Okay, so right here is just kind of viewing pairs. Let's see if I can start the activity. And kind of go. Ignore the rules at the top. Let's see, view pairs. Oh, these are the answers. And so we'll just kind of go through them here. All right, so when I look at this, I look at 3,000. Well, there's no decimal, so I'm going to be thinking of my Pac-Man. And here comes Pac-Man. He's going to eat through, and sure, I only have 1. Here, Pac-Man once again. Eat through, there's 1. Well, I come here, here's my Pac-Man on both ends. I see numbers, which are my ghosts. And I do have a captive 0, but he can't get to that 0. So I have 3 significant figures. Pac-Man. So I've got 1, 2, 3, 4, 5. 5 significant figures. Pac-Man. And sure enough, only 2. And then I come here, and Pac-Man's like excited, but then he's like, oh, there's a decimal. I can't do anything with that decimal. All right, so that's 3, 6, 7, 8. 8 significant figures. I like Pac-Man rule. It just makes it easier for me. Hopefully it's easy for you too. All right, so now let's go ahead and do some more. Let's do some metric conversions. I know we didn't have any earlier in the set, so this is where we're going to kind of work them through. I like to work them using the exponents. When I look at a picogram, I'm going to go over to your table in your textbook on page 10. For those of y'all who are using the electronic version, you'll see it on the notes as well. I like to use a little math formula where it's E1 minus E2. And these E2s right here is going to be my exponents. That's what I'm really looking at. So when I look at a pico and I have a micro, it's telling me how many picograms are in a microgram. So I'm going to look at 1 microgram. And I'm going to go ahead and convert this into a picogram. Well, my exponent for a pico is going to be a negative 12. My exponent for a micro is a negative 6. So now I'm going to plug it down here into this equation. I'm going to say negative 6 minus a negative 12. Well, what does your math rules tell you? A negative minus a negative equals a positive. Good job. So I'm going to say negative 6 plus 12 equals a positive 6. So now, if it's positive, I go to the right. If it's negative, I go to the left. Well, because it's positive, I'm going to the right, so I'm going to go ahead and make 6 jumps. Let me go, let's do, I don't know, green. 1, 2, 3, 4, 5, 6. Fill this in with zeros. 1, 2, 3, 4, 5, 6. There's my answer. 1,000,000 micrograms. That's a lot. 3, 4, 5, 6. All right, so 1 microgram is equivalent to 1,000,000 micrograms. Simple. All right. Now, if I come look at this next one that I've kind of written all over, and I'm going to run out of room here. I wonder if I could just go back and forth. Oh, I could just erase it. I'll erase it. Okay, I'm going to leave my equation alone, but I'm going to erase all this so I can kind of see underneath it. I'm going to leave my right and left rows, but everything else, I'm going to pop it out. All right, so same rules. Nano is going to be a negative 9, and a mega is going to be a 6, positive 6. So same rules apply. I'm going to go, I want to know how many megameters are in a nanometer. So I'm going to put it right here, 6.5 times 2 megameter into a nanometer. And I decided to rewrite it because I didn't want you guys to think like this was the first one, this was the second one, because megameter is actually the first one. So we said that the exponent for a mega is a 6. I'm going to say 6 minus the exponent for a nano is a negative 9. So I'm going to put that there, negative 9. So I'm going to go ahead and add it here. 6 plus 9 is 15. So that tells me my exponent needs to move 15 times. Because it's positive, I'm going to go to the right again. All right, so now if I want my answer to be in scientific notation, this is an actually pretty easy rule here. I'm gonna show you, and then I'm gonna kind of break it down. Because they're exponents and they're power to the 10, and I'm just basically moving my decimal over each time I'm seeing this, I can do it really easy and say 2 plus 15 is 17. So my answer is 6.50 times 10 to the 17. Done. But for those of you guys who are looking at me like, whoa, what'd you do? How'd you get that? So if I break this down here, this times 10 to the second basically is like saying I have 650. I have 650 micrograms. That's all I did. And when I did my exponent jumps, I'm seeing I have to jump 15 times. Well, let's just change into an orange. Well, right now my decimal is right here, and I'm going to jump 15 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I'm going to fill in zeros here. I'm going to try to fill in zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And if I want to put it in scientific notation, I'm just going to count and move myself back. Because remember, the rule says the number in front of the decimal should be between what and what? Perfect, 1 and 9. So I'm just gonna, let's go in red. I'm gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and my decimal goes right there. Okay, and exactly what I did. So I went ahead and did longhand, but that's kind of a nice little shortcut when making these conversions. Hopefully you like that trick. Okay, so I'm gonna go ahead and erase it. Now looking at this last one, this one is actually pretty easy when you start looking at the conversions. There's not much to do with it at all, because if you look in your textbook on page 10, it's going to show you the conversion factors on there, and it tells you that 1 decimeter is going to be equivalent to 1 liter. So I'm just going to write that down there. So 1 liter equals 1 cubic decimeter. So when I say how many liters are in 8 cubic decimeters, well, that's easy. It's a 1-to-1 ratio. 8 liters. And that's all. Hopefully you guys, y'all have any questions, please feel free to send me a message through the Remind. It's the easiest and best way to get a hold of me. I can respond pretty quickly. Other than that, hopefully it's a nice little review from what you all learned last year. Hopefully we're good. All right. Bye, guys. Love you all.